naturally, the first thing that comes to our mind is the ability of the transport layer to multiplex different user streams coming from various kinds of data traffic sources. So in this module, we shall quickly have a recap of how multiplexing is implemented through a multiplexer on the sending side and a demultiplexer on the receiving side. It is important to highlight here that we are talking about the logical operation of multiplexing and demultiplexing, not the physical layer multiplexer and demultiplexer that are implemented at the hardware. Then we'd look at the support we get to multiplex using the port numbers in TCP and UDP. And if we were to put a cost on multiplexing, if we look at this figure, we'll understand that we have various processes running on the sending side of a single host. Likewise, we could have multiple hosts, each with multiple processes running. So the multiplexer takes data from all of these processes and in a systematic way puts this data, which is intertwined, interleaved data from all of these sources, onto a single connectionless IP network. On the receiving side, both at the network level and at the host's level, we have demultiplexing carried out. This demultiplexing assigns respective data to respective destinations in such a way that there is no confusion between who sent data to whom, and the multiplexing carries out transfer of data from various sources to various destinations in a smooth manner. In various headers, particularly at the transport layer, the TCP and UDP headers, we have allocated 16 bits for port number. Now, since it is an unsigned integer, we have a total of 65535 as the upper bound on the maximum number of ports that can be established. So it means this much is the total capability and an upper bound on the number of multiplexed sessions that could be accommodated. An interesting paper that explores the working of data centers gives us a close understanding of how resource multiplexing can be put to advantage. So what they recommend is to assess the benefits of resource multiplexing in data centers. In this paper, an interesting figure is presented, which is on the time and resource allocation plane. In this two-dimensional figure, you can see if there is a user requirement or requirement coming from various users, and if that is time varying and the number of resources and the volume of resources varies with time, you can consider it like an analog representation shown to you here. If exactly what is required is allocated, it means the multiplexing has to be almost perfect. So the optimal allocation would follow the resources on the network using this analog graph. But in reality, multiplexing, number one, has its own overhead, and number two, approximates the resource requirements of individual users in a shared environment. So if the resource allocation is overly crude, you'll see the coarse-grained resource allocation where the step size is large, and on the y-axis, the resource allocation is done in a very coarse way. But if resource allocation is done with a smaller step size on the time axis, and again a smaller step size on the resource allocation axis, we'll see fine-grained allocation. With these options of allocation, we can understand that multiplexing would have some kind of overhead that it imposes on any shared system.